Massless pulleys are like ropes. They show up in a lot of introductory physics problems, and the authors pretty much expect you to know everything about them. But if you haven't worked with them very much, they can make moderately difficult problems almost impossible. I'm going to take a look at massless pulleys and then use them to get more practice using Newton's second law in one dimension. Pulleys redirect a tension force. If they are massless, that still means the tension magnitude is the same everywhere. So here I have a picture of two masses, mass A and mass B, connected by a string over this pulley. And if that's massless, then we would expect the tension in that part of the string to be equal to the tension in this part. So let's do an example. If we assume the surface is frictionless, what is the acceleration of mass B if only the masses are known? Well, I want to apply Newton's law to this problem. And Newton's second law means I have to choose an object. So I'm going to choose, first of all, mass B. That's the one that I want to know the acceleration of. I'm going to isolate it and then find all of the forces on mass B. Well, the only thing touching mass B is the string. And so there's a tension force, and then there's the force due to gravity. So now I want to sum these forces. I'll use a free body diagram representing the object as a single point, the vectors pointing in their appropriate directions with their tails at the point representing the object. I must have a coordinate system and a positive direction for my free body diagram. Now, typically I've been pointing my positive direction up when I have a vertical system, and I'm going to choose down for this one. And it's pretty easy to see why if you go back to get a clear visualization of what's happening in the problem. If this surface is frictionless that mass A is on, then I'm fairly confident that mass B is going to pull mass A across the surface while it falls. So I think mass B is going to accelerate downward. And if it does, if I have my positive axis downward, then my acceleration will be positive. So now I want to sum those forces and set them equal to the mass and the acceleration. So I've written out the vectors in vector form. There's the tension, which has a magnitude of t, and it points in the negative x direction given this coordinate system. And it's added to the force due to gravity, which has a magnitude of the mass of mass B times the acceleration due to gravity, and it's pointing in the positive x direction given this coordinate system. The vector sum of those two forces is equal to the mass times the acceleration, which is also a vector. It has a magnitude of mass times the acceleration, and it's in the positive x direction from the context of the problem. Note that this is the mass of block B and the acceleration of block B, which I've identified with B subscripts. Since I have multiple masses, I want to be able to identify which is which. And in Newton's second law, the vector sum of all the forces on one object is equal to the mass of that one object times the acceleration of that one object. This I can translate into a scalar equation given my notation for vectors in one dimension. The sign in this case gives us the direction that it's pointing. So mg is positive, t is pointing in the negative x direction, it's equal to mass times the acceleration. Do I have enough to solve? I'm told I know the masses, I know g. I'm trying to find the acceleration, but I don't know tension. I do not have enough to solve. But that's okay, because I have another object. I can use Newton's second law on mass A to come up with another relationship for my parameters. So now I'm going to choose a new object. I'll choose mass A, and I'm going to isolate it. I'm going to find all the forces on it. There's only one force in the horizontal dimension in this problem, which is tension. Now, in my model of sliding things that I set up when I'm only working in one dimension, I'm ignoring all the forces in the vertical dimension. Since the object is constrained only to move horizontally, I'm only considering those forces. And there is, of course, a contact force between the surface and mass A, but I was told it was frictionless, and that means the component of that contact force in the horizontal dimension is 0. So the only force in the horizontal dimension is the tension. So there's just one force, just my free body diagram with just one force pointing to the right. I've established a coordinate system that's positive to the right also, because I think mass A is accelerating that direction. There's my vector, is the tension. So that tension is equal to the mass of A times the acceleration of A. They're in vector form. Translating that with my one-dimensional notation for vectors, it's in the positive x direction, and then is just equal to the mass of A times the acceleration of A. So now I have two relationships, but I have three unknowns. There's the tension and the acceleration of A and the acceleration of B. Is there context from the problem itself that can give me a relationship between A and B? They are connected by a string, and our string model says that the string doesn't change length. So the length between MA and MB is always the same. I want to solve for A, so I want to move this term over to the other side. And now I can factor out an A on the right-hand side. And now divide both sides by the sum of the masses, and I get my solution for A. Before I do anything, I want to check to see if this makes sense. I have mass of B in both the numerator and denominator, but in the numerator, it's going to go up by a larger fraction than in the denominator because of the sum. So as mass B increases, the A increases. And of course, mass A only shows up in the denominator, so as it increases, A decreases. That makes sense, and so I believe that I found the right answer. If I had numbers, I would plug them in now after I've checked to see that this made sense.